Alright, so in this video, we're going to go over some rules on how do we take the derivative. So in the previous video, I went over the definition of a derivative, and it's based off the limit. Well, thank goodness there are actually some rules here that can help us find a derivative more quickly. Okay, and so here we go. So the first rule I want to go over is the constant rule. Okay, and so you're going to actually see this notation throughout the video that I'm highlighting. So d over dx, what that is called an operator, meaning it does something to a number, to a function, right? And so d over dx is the excuse me, the derivative operator. So anytime you see d over dx, it just means take the derivative. Okay, so nothing fancy there, it just means take the derivative. Well, it turns out that if you take the derivative of any constant, in this case which we're calling c, its derivative is 0. Okay, so c is a constant function. So the derivative of any constant function is 0. Okay, so some quick examples. For example, suppose f of x is equal to a negative 134. Okay, and let's say we want to take a derivative. Well, this f of x is a constant function because there's no independent variable, in this case x, attached to that function there. So this is just a constant function. So the derivative of a constant is 0. So the derivative of any constant is 0. Really quickly, so why is that the case? Okay, I can give you a 2-second proof here. So a constant function, so think of if you had to graph the function y equals a negative 134, right? So a constant function is a horizontal line. And so remember, the derivative gives us the equation of the slope of the tangent line, or the instantaneous rate of change. But if you notice, if you have a horizontal line, nothing is changing. So therefore, what's the slope of a horizontal line is 0. Therefore, the derivative of a constant function is 0. Okay? So if you have a constant function, meaning there's no independent variable attached to it, its derivative is automatically going to be 0. All right, next one. Now, let's say we wanted to take the derivative of x raised to some power n. So what's the derivative of x raised to the nth power? Well, to perform that derivative, we're going to do something called the power rule. And what the power rule says is when you want to take the derivative of x to some power n, what you do is you bring out that exponential power, you bring out that power n, and it multiplies your variable x, but it's now raised to the one less power. You subtract away 1 from the power. Okay? Some quick examples. Suppose f of x is equal to x cubed. Well, the derivative, f prime of x, okay, so our n, our power is 3. So the derivative says you bring the power out front, you bring our 3 out front, and it multiplies x, and I subtract 1 from the power. And so now it's 3x to the second power. Okay? Let's try another example. What if it was f of x equals, how about this, 1 over x to the 5th power? Let's say we have that. Okay? Well, in order for us to apply the power rule, it has to be in the correct form. And the correct form is x to some power n, not 1 over x to some power n. So our first step here is to rewrite this function. And what we're going to use here is a property we know from algebra. In algebra, we know that if we have 1 over x to the nth power, and if we want to rewrite that, meaning take that exponential function x to the n, okay, and bring it to the opposite location, we know that we take the opposite of the power. So 1 over x to the n power is the same thing as x raised to the opposite of that nth power. And so what that means is that suppose we have, I don't know, a 1 over x to the 4th power. And if we want to rewrite that, when we bring that x to the fourth to the numerator, it becomes a x to the negative 4. And it's being multiplied by the understood 1 that's up in that numerator. If you want to write the 1, that's perfectly fine. Also, if we have 1 over x to the negative 3 power, let's say I want to rewrite that as x to a single power, it's going to be x to the positive 3 power. So I'm taking the opposite of the power because I'm moving it to an opposite location. So when we come back to our example on the left here, the 1 over x to the fifth, when I rewrite that, when I take that x to the fifth and I bring it up to the numerator, I need to take the opposite of its power. And notice my notation here. I'm writing f of x because I am not taking a derivative. What I'm doing here is I'm just rewriting my function. I'm trying to get it prepared in order for me to be able to take the derivative. And now I'm able to take the derivative because it's in the correct form for a power rule. So f prime of x is equal to, let's see, our power comes out front. So we have a negative 5x raised to the subtract 1. So be careful. Negative 5 minus 1 is a negative 6 power. Be careful with those negatives. Okay? So this is a correct solution. Or what if we wanted to rewrite it where the power on the x was a positive value? Well, what that means is I could take that x to the negative 6. Currently, it's assumed to be in the numerator. What I could do is I could actually move it down to the denominator. And this answer is equivalent to a negative 5, which has to stay in the numerator because the power is not attached to it, over x to the positive 6 power. These are synonymous answers. These are both correct. All right. Another kind of power rule here is that oftentimes we're going to be dealing with radicals. So it's also important that you know how to rewrite your radicals. So if you come over to the far right side here, the rule for rewriting radicals is that if I take the nth root of x to the nth power, it's x to the m over n power. So I get that rational or fractional power once I deal with radicals. So for example, the square root of x. Okay? With the square root of x, the index, the number that's supposed to go in that radical there, is an understood 2. Hence the name square. Square means second power. So the index is 2. The power on the x is understood to be a 1, right? So square root of x is the same thing as x to the 1/2 power. All right? The square root of, let's say, okay, how about this? What if we took the fourth root of x to the third power? What would that be as a fraction? Or excuse me, as a rational power? It would be x to the 3/4 power. Okay? So I can't emphasize that enough. Know how to rewrite your fractions and know how to rewrite these radicals. They're going to come up a lot in this course. So, for example, suppose f of x is, let's say it's 1 over the square root, or let's just do a basic one. Let's do square root of x. Okay? In order to take this derivative, what I'm going to do is I'm going to rewrite my square root of x for the reasons we just discussed. It's going to be x to the 1/2 power. Okay? And now I'm ready to apply my power rule. The power rule says f prime of x equals, well, let's see what happens. The power comes out front, so 1/2 is times x. And what I have to do is I have to subtract 1 from the original power. So I'm going to come over here on the right side. I'm going to do a little bit of side work here. So 1/2 minus 1, you guys know how to do the subtract fractions, right? We have to get the same denominator. So 1 is the same thing as 2 over 2. So 1/2 minus 2 over 2 is a negative 1/2. So 1/2 minus 1 is a negative 1/2. So there we go. So the derivative of x to the 1/2 power is a 1/2 x to the negative 1/2 power. Or if we wanted to write this alternatively, I could take that x to the negative 1/2. All right. So right now it's currently assumed to be in the numerator with the 1. If I want to get a positive power for the x, I can move it to the denominator and it can combine with the 2 that's already down there. So this is also an equivalent answer. All right. Okay. And then one more, and I'll go to the next rule. One more. Let's kind of put a few of these together. What if it was 1 over the square root of x? Okay, 1 over the square root of x. So the first thing I want to do is we want to, let's rewrite that radical. So the square root of x, we know that's x to the 1/2. Okay. And then we have a fraction, and we know the drill to rewrite that fraction. I need to take that denominator. I need to swing it up to the numerator. So rewriting that, I get 1 times x to the negative 1/2 power. Notice this is not the derivative. This is just us preparing the function to have its derivative applied. Now we apply the derivative. So f prime of x equals the negative 1/2, which the power comes out front, and then x, I need to subtract 1 from the power, right? So the original power, let me get a different color here. The original power was a negative 1/2, and I'm subtracting away 1, which we know from before. 1 is a 2 over 2. So a negative 1/2 minus 2 over 2 is a negative 3 over 2. So the power on our derivative is a negative 3/2. Okay? And for the reasons we discussed earlier, I could take that negative x to the negative 3/2 and I can move it to the denominator. This is the same as a negative 1 over 2x to the positive 3/2. Okay? Once again, both of these answers are equivalent. I want you guys to be comfortable seeing what both these answers look like, because when you go to your homework, they may have it written one way that may be a little slightly different than the way that you have completed in your work. All right, so that is our power rule. So notice up to now, we've assumed that we've had a constant of 1 multiplying every single x value here, right? So here there's an understood 1, right? Here there was an understood 1. Here there's an understood 1. So there's been a 1 everywhere. So what happens if you have something other than a 1 in front of that x and you want to do the power rule? Well, in that case, we call this the constant multiple rule. So it says, what if you have a constant c times x to the n power? Well, what happens is, and you can kind of almost predict this already, the n comes out, the power comes out, and it multiplies the constant that's already out there. So the constant doesn't go away. So the key here is that this is a constant multiple. It's not just a constant function like the first rule that we talked about. Okay? So for example, suppose we have f of x is equal to 4 x squared. Okay, let's say we have 4x squared. So what's the derivative? Okay, well, what happens? The constant multiple rule says, listen, that 4 is going to multiply whatever the derivative of x squared is. And so the derivative of x squared is, let's see, 2 comes out front. X is now raised to, we have to subtract 1 from that second power, and we have an understood 1 there. I'm not going to write the 1. You can if you want to. And then what's 4 times 2x? 4 times 2x is an 8x. So that's what that constant multiple rule is saying. It's saying, look, you take your exponent, it multiplies your constant, multiple out front, and then you subtract 1 from the power. Okay? Ooh, how about this one? What if we have f of x is equal to a 6x? Okay? Let's do the constant multiple rule. What happens? So what's the understood power on the x? The understood power is a 1. So 1 comes out front and multiplies 6. So let's see, 6 times 1. And now x should be raised to the 0 power, right? Because I need to subtract 1 from the exponent on the x. Well, look, folks, anything raised to the 0 power, at least in this course, is not 0, but it's going to be 1. So what we have here is that x to the 0 power becomes a 1. So we have f prime of x equals 6 times the 1, which came from the power earlier, times the another 1, which is the x to the 0. And 6 times 1 is equal to 6. Hey, and folks, here's a cheat code. Notice, remember, derivatives are slopes of tangent lines. So if my function is 6x, that's already a linear function. That's already a linear function. So the slope of that linear function, right, is going to be the same thing as the derivative. So if you have a function where the degree is 1, where it's a linear function, it's the derivative is always going to be that constant multiple that happens out front. Okay. One last rule. is the sum and difference rule. So up to now, we've only been taking derivatives of one single term, x to some power. Well, now the question becomes, what if you have multiple terms? And that's what the sum and difference rule says. It says if you want to take the derivative of multiple terms, you just simply take each individual derivative. That's what the sum and difference rule is telling you. For example, suppose f of x is 5x to the third plus 2x squared plus 6x minus 5. Okay? I want to take the derivative of this function. So what do? We do the sum and difference rule. I like to refer to the sum and difference rule as a piece-by-piece rule. What that means is that I'm just simply going to take the derivative of each individual piece separately and combine my results. What does that mean? Here we go. F prime of x. What's the derivative of 5x to the third power? Well, the 3 comes out front and multiplies 5, and it gives us 15x to the second power. Plus, what's the derivative of 2x squared? 2 comes out front, multiplies the 2, and that gives us 4x to the first power. We're subtracting 1 from the power. Plus, what's the derivative of 6x? Derivative of 6x is just 6. Okay, to see that, go back to the previous, previous problem that we did. Right, what do we say? The derivative of a 6x is 6. Okay, and then lastly, the derivative of a negative 5. Negative 5 is a constant term. So remember, the very first rule that we talked about was a constant rule, right? So the derivative of any constant is 0. So the negative 5, it doesn't drop off. It just turns out that the derivative of negative 5 is 0. And there we go, folks. That is our derivative via the sum and difference rule. All right, my hope is that this can get you through your next homework. I'll see you guys in the next video.